Hello everyone and welcome to my newest video where I talk about stiffnesses, which is one of my most favorite topics to talk about. Because it's a very big and complex topic, in today's video I will focus on the initial stiffness, which from practical point of view I think for first step it's okay and it's enough. And in today's video I will show you how to perform a stiffness analysis in idea statica. Then we will take the value for the initial stiffness of that connection and we will apply it on a joint in SCIA engineer, and then we will see what changes will happen in the global analysis of that model. But before I move to my model in SCIA Engineer, first I will give you some intro of why stiffnesses are so important and what changes to expect when you change the stiffness of a certain node. So today's example will be the stiffness of a fixation of a column, and this column will be part of a very simple frame. And as we all know, we can encounter three different situations when we are talking about classification or stiffness classification of a joint. So it can either be a hinged joint or, in this example, a hinged support. And this type of support cannot take any bending moments. This is an example of a connection of a hinged support. Then we have the fixed support or a rigid support. This type of support can take bending moments to their full extent. And this is how it would look like in SCIA Engineer. And then we have something in between. And this is an example of a semi-rigid joint or semi-rigid support. And this type of supports take bending moments to some extent. In SCIA Engineer, they would look like this, where we would input the stiffness value or their initial stiffness value in some of the axes. And normally they will have some cross indicating around which axis we applied a certain stiffness. So if we have hinged supports, this is how the diagram of the bending moments would look like, and we will have a zero bending moment into the supports. Then if we have rigid supports, we will have the maximal bending moment, which in this example is around 20 kilonewton meters. And last, if we have a semi-rigid support, then in that case we will have something below the value of 20, and in this example it's around 40 kilonewton meters. And this is very important, especially in the deformation of the frame, because when we have hinged supports, then in that case we will have maximal deformations into the columns as well into the beams. On the other hand, if we're working with fixed supports, we will obtain the minimal possible deformations. And if we are working with semi-rigid supports, then in that case we will have deformation in between these values, or in between the maximal and the minimal value. So now let's go to the SCIA model and see how we can practically do this. So I have prepared a very simple SCIA model, and first I will start with the rigid supports, and you can see in here that the supports are set as fixed. Normally when we do stiffness analysis, the loads are not of importance, so I will run a calculation. Okay. And I have some random loads into the model. So let's see what happens when we see the diagrams of the internal forces, especially the diagrams of the bending moments. In the column or in the support, we have a value of 20 kilonewton meters, which is the maximal value. And if I go to the deformations, I will change now to combination SLS, and then I will switch to the total deformation, and instead of global I will set to member. Let's refresh this. You can see that we have 2.2 millimeters deformation in the column. Now let's close this, and I will export this node to IDEA Statica to perform a stiffness analysis of the connection. So I will write here IDEA, and I will look for the joint input. Okay, I will select this node, escape, and now I have the attribute of the node. If by any chance you're not seeing this attribute, you will go to right click, then view settings for all entities, and we will go to attributes, and you will have to select it in here. So normally this is how you hide it or preview it. Okay, and now I will go to IDEA, and I will go to connection check. And like I already said, the loads are not of importance when we perform stiffness analysis, so I will simply leave it like it is, go to export to IDEA, and then select this attribute. And now we're performing export from SCIA to IDEA. You can do this from scratch as well, so start blank in IDEA Statica, but for me it's easier this way because I will get the original section that I used in SCIA Engineer exported to IDEA Statica, and also I can have the same orientation of the column in IDEA. So let's start from here, and we will move to down. So for first one, we will have to select the analysis type. So instead of this analysis, I will switch to stiffness analysis. Next, I will move to the members, and I will have to select which member will be the analyzed member. But in this example, we only have one member, so we don't have to worry about it. It's already selected as analyzed member. In any case, if you're working with more than one member, make sure to select for which member you are calculating the stiffness. And then I will go to load effects, but like I said, these are irrelevant, and I will delete them, and I will apply the correct one later. So now I will go to operation, and let's do the design of the connection. I will choose a very simple example of a connection. So this is a base plate connection, and let's choose the anchors. So I will choose M24 8.8. Okay. Okay, let's see it in plan view. The connection looks something like this, and let's imagine that this is the correct design of the connection. So in reality, this is how our column is supported. And now I will move to the load effects, and I will move to the first load case. So now we will have to apply the loads for the stiffness analysis. First, I will set the preview on for the axis. And now we will have to decide around which axis we will perform stiffness analysis. So let's say that we want to perform a stiffness analysis around the strong axis of the section, and that would be around M epsilon. I will change the name to M epsilon, and I will have to insert a value of the stiffness in here. This value, I will set it on of 1.5, and this is a random value. And this is because whatever value you apply in here, you will always get the same initial stiffness. So you can input any random value that you can think of. And this is all that you need if you want to calculate the stiffness around epsilon axis. Because this is a symmetrical connection, the direction of the value is not of importance. But if you're working with a non-symmetrical connection, then make sure that you apply the value into with the correct sign, And if you want to work, in example, calculate the stiffness in the opposite direction, then you will have to apply minus 1.5. If you want to calculate, let's say, the initial stiffness around the weak axis, then in that case you will have to create new load, and in the new load you will have to insert the value here. Like I said, again, a random value, and everything else you will have to leave on 0. But now I will deselect this because I only want to calculate the stiffness around the strong axis, and I will run the calculation. Because this is a very simple connection, normally it will be a fast calculation. So now we have the results, and the results that we need will be in check, and I will go under rotational stiffness. And now we have two types of results, a table results and also a preview of a diagram result. So everything that you have in the tables, you will have it on the diagrams as well. And we need the initial stiffness value, and that is 4 meganewton meter radians. So let's remember this value, and now I will go back to my SCIA engineer model. Okay, I will close this. And now let's select the fixations or the supports. I will rotate a bit to make sure that we are previewing it better. Okay, and now we will have to decide around which axis we will apply the stiffness that we already calculated in Idea Statica. Like I said, we were calculating the stiffness around the strong axis of the section, and that would be around epsilon again in SCIA. So this is here, and instead of rigid I will switch to flexible. But before I insert any value here, I will have to make sure that I match the same units that I used in Idea Statica, and right now you can see that this is incorrect. So I will have to go to unit system, manage units, and under stiffness, under force, I will switch to meganewtons. Then under length, I will switch to meters. And under angle, we have the radians, but this is correct. So I will click OK. So now we have the same units, and I will input the value of 4 in here. Okay, and you can see that now we have this cross, meaning that we have a certain stiffness around this axis. Okay, let's put it again in this view, and I will rerun the calculations again to see which changes happened into the model now. Okay, okay, deselect this, and I will go first into the diagrams of the internal forces. And we have the diagram set as m epsilon, which is okay, and I will refresh it. And now instead of 20, we have a value of 7.40 kilonewton meters. Also, we can check the deformations, so let's see the total deformations. And you can see that the deformation slightly increased from 2.2, now we have 2.7 millimeters. And that's how we input the correct stiffness into the supports of these columns. If by any chance these results are not okay, let's say we exceed the limit of the deformations, then we can reinforce the connection in here to get bigger initial stiffness. So we should go back to Idea Statica. We should propose another solution for this connection. We will recalculate, get a new initial stiffness, and then we will go back to the SCIA model and try to see if we get better results with the new initial stiffness. And this is all that I've prepared for today's video. I hope you find this useful, and see you in my next video. Bye.